Hello, this is Math 2115 coming to you from the College of DuPage, and the title of this lecture is Proofs by Resolution. I encourage you to be an active learner as you work through these videos. We're going to talk some about the work of John Allen Robinson. Here's his picture. He started at Cambridge and then went to the University of Oregon when he left the UK, coming to the US. And then he went to Princeton and he got a PhD in philosophy. He worked at DuPont, the chemical company, as an operations research analyst and learned programming there and taught himself mathematics. There's a lesson there that you will be a lifelong learner. He moved to Rice in 1961 as a faculty member and spent his summer as a visiting researcher at Argonne National Laboratory, which is close to us in Lamont. It's located in Waterfall Glen Forest Preserve. This is a picture of the waterfall that is there, and this is a huge place, and I have hiked around this, and it's a 10-mile hike if you go all the way around. And they do research on physical science, life science, environmental science, energy science, photon science, data science, and computational science, and math is behind all of this stuff. That is a great place for you to get an internship in any of those fields. In this section, your author chooses to write A and B, or A conjunction B as AB. Resolution, then, is a proof technique proposed by J.A. Robinson in 1965, and here's what it says. If P or Q and not P or R are both true, then Q or R is true. And we can verify this using a truth table, and I'm going to ask you to do that in a bit. It turns out that this is the basis of many computer programs that reason, that is, think, and prove theorems. In a proof by resolution, the hypothesis, this is the if part, and the conclusion are written as clauses, and a clause consists of terms separated by ors, where each term is a variable or the negation of a variable. So you can see you've got ors everywhere in the statement there. Let's, before we move on, let's have you prove this. So you're proving the principle of resolution. You know what to do. Let's see how you did. So what you do is you build a truth table, and this is the truth table you have to build, and then we cross out everywhere where these are false. So I crossed out, this is down here is where P or Q is false, and up here is where not P or R are false. And then after I cross out all those places, I see if these things being true force this to be true. And when you look at the final column, Q or R, you say, yes, it is true. That's what you were supposed to do, and that's something that you want to have as in your toolkit. A direct proof by resolution proceeds by repeatedly applying that principle, and this is the principle again, to pairs of statement to derive new statements until the conclusion is reached. Now, if a hypothesis is not a clause, it must be replaced by an equivalent expression that is either a clause or the end of clauses. And so, for example, you often will use De Morgan's law, and you will change if-then statements to equivalent statements without the if-then notation. And notice down here he's using this notation because you see this would be negation A and negation B, and he's just putting them next to each other as we show on the earlier slide. And the negation of A and B is negation A or negation B. That's De Morgan's principles. Now, it can be shown that a resolution is correct, and refutation is also complete. Resolution is correct means that if a resolution derives a contradiction from a set of clauses, the clauses are inconsistent. Resolution is refutation complete means that the resolution will be able to derive a contradiction from a set of inconsistent clauses. Thus, if a conclusion follows from a set of hypotheses, resolution will be able to derive a contradiction. Unfortunately, resolution does not tell us which clauses to combine in order to deduce the contradiction. A key challenge in automating a reasoning system, that is a computer system that thinks by itself, is to help guide the search for clauses to combine. And here are some references that deal with that. So, to construct a resolution proof, first replace any of the hypotheses or conclusions that are not a clause with one or more clauses. Then replace pairs of hypotheses of the form P or Q, not P or R, and Q or R until deriving the conclusion. Remember that resolution can be combined with a proof by contradiction. So here's a problem I would like for you to do. And remember, and don't do this as a truth table. I want you to use a proof by resolution to do this. So it's going to be a narrative proof. It's not going to be a truth table in this case. You know what to do. Let's see how you did. All right, the first 3 steps of your proof are just above the line before we go, therefore, to the conclusion. So the first 3 steps are exactly these steps. But then, here what we have is R or not P, and not or R or Q. So you see by the principle, if we look at 1 and 2, we've got R and not R, so that tells us that negation P or Q must be true by the principle of resolution. And now if you look at 3 and 4, what we have is that this is not P or Q, but then P, that means that this is false. That forces Q to be true. That's one of our fundamental logic arguments that is valid. And so we've finished this problem. This is problem 3 in your book. Here's problem 4 in your book. You know what to do. Let's see how you did. This one's more involved. Okay, so this is one of the statements we started with. This is one of the statements we started with. This one we have to break into because we have to use a distributive property here, because you see this is S and T, so that means not R or S, and this also means it is not R or T. So that we broke that into pieces, and then this is that last statement. Okay, now when we look at 1 and 5, so here is 1 and statement 5. You see this is not P or T, and this is P or all of this business here. So you see the principle of resolution tells us that the conclusion is going to be T or all of that statement. So we have that. From 2 and 6, we see that here we have not Q or S. And in 6, we now have Q or this business, T or R or U. So that means that what we can deduce from that is that it must be S or T or R or U. But now we're going to look at statement 3 and statement 7. You see statement 3 says that this is not R or S, and down here it says it is R or S or T or U. So that means by the principle of resolution we can have S or T or U, and that's what we were supposed to prove. This requires a little bit of thought, I think. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. God bless you all.